In this video, I will address sections 10.7 and 10.8. I would like you to start with this warm-up. Press pause on your video, and when you're ready for the answer, press play again. Here are my answers. So in the first problem, you had to draw yourself a diagram. It says I have a circle O. The first thing I did was draw myself a circle. Had a radius of 12. And asked how far from the center of the circle is a chord with length 12. So what I did was I drew in a segment, and I drew in the distance from that circle. Remember, the distance from the center to a segment is a perpendicular distance. So this segment here that's perpendicular will bisect that chord. That's one of the theorems. And the secret to doing this kind of problem is to always draw your radius from the center to either end point of your chord. Now that you have done that, you have a nice right triangle, and you can label your radius 12. You can see that I used Pythagorean theorem, leg squared plus leg squared is hypotenuse squared, and I went through and solved. I found that x squared was 108. I took the square root. I got plus or minus the square root of 108, and you will note that since it's a distance, it has to be positive, and square root of 108 simplifies to 6 square root of 3. Now, one thing I want you to know too, as you look at this, you could recognize this as a 30, 60, 90 triangle. If you recognize that you have a hypotenuse that's double a leg, this matches your 30, 60, 90 pattern here, and your other leg would be a root 3. So you can see here that this is 6 square root of 3, and that would mean, just so you know, this would have to be a 60-degree angle. This would be a 30-degree angle because the shorter leg is opposite the smaller angle. A root 3 is opposite the 60-degree angle. So clearly in my diagram's not drawn to scale. And you didn't have to recognize it as a 30, 60, 90 triangle in order to solve the problem, but I thought I would mention it. Now, the next problem was a walk-around problem. We are told that Fn is 20. NU is 14 and FU is 12, and you notice that I labeled all of my lengths. They're all circles that are tangent to each other, as shown in the diagram, and I want to find the radii of all three circles. So I had to start with one of the radii, and I just chose this one here, and I labeled it X because I didn't know what it was. Then if this entire length is 20, I know that this length for my radius of n is 20 minus x. And since all radii are congruent, this segment here is also 20 minus x. Now I know this entire segment's 14, so my segment here, that is the radius of u, would be 14 minus the 20 minus x, and then I distributed the negative, and I got minus x plus 6. And over here, I represented that as x minus 6, same thing. And this is the same radius in circle F as I started off with, so this is x. Then I know that this segment here, which I've highlighted in yellow, has to be 12. Well, if I add those two pieces together, it has to be 12. I went through and I solved for x. Now I know the radius of F is n, or F is x, so it's 9. And then I know the radius of u is x minus 6, so x is 9, so it's 9 minus 6, or 3. And the radius of n is 20 minus x, so it's 20 minus 9, or 11. Now, some definitions in this section are inscribed and circumscribed. So I have some diagrams drawn in here. It says triangle ABC is inscribed in circle O. So ABC inscribed. Notice this triangle is inside circle O. inscribed. The definition says a polygon is inscribed in a circle if all of its vertices lie on the circle. So you can see each of these vertices is on the circle. It's inscribed. Now, circumscribed says this polygon PQRST is circumscribed about circle F. Now, notice a polygon is circumscribed about a circle if each of its sides is tangent to the circle. So you can see here PQ is tangent to the circle, QR is tangent, SR is tangent, TS is tangent, and PT is tangent. Now, notice these are some pretty special points that we have drawn in here, the centers. It's going to be called something special, but I just want you to notice here. The center of that circle, O, is equidistant from the vertices of my polygon that is inscribed in it. If I have a polygon circumscribed about a circle, the sides are the same distance from that center because a radius, remember, is perpendicular at its point of tangency. Now, these points are called something special again. The first name is a circumcenter. The circumcenter is the center of a circle circumscribed about a polygon. It's called the circumcenter. So I have the circle circumscribed about this polygon, my triangle T. T is the circumcenter. Now I have a pentagon inside the circle. The circle is circumscribed about this pentagon. P is the circumcenter. The centers of the circle that are circumscribed about a polygon are called the circumcenter. And the circumcenter is equidistant to the vertices. The next point is called the incenter. The center of a circle inscribed in a polygon is the incenter of the polygon. So notice, this circle is inscribed in my triangle. M is the incenter. This polygon, PQRSTU, is the circle's inscribed in that polygon. F is the incenter. These are the incenters. The incenters are equidistant to the sides. Now, there's a theorem involving inscribed and circumscribed polygons. The first theorem is if a quadrilateral is inscribed in a circle, its opposite angles are supplementary. So, angle 1 and angle 2 have to sum to 180. They are supplementary. Angle 3 and angle 4 have to sum to 180. They are supplementary. Now, let's think about why that is. Remember, as I look at angles, inscribed angles, where my vertex of my angle is on the circle, I know that this angle, angle 1, is 1/2 of this arc. Now, if I look at angle 2, it has the same kind of situation. Angle 2 is half of this arc. Well, both arcs added together are 360 degrees. So that means that if each of these is half of those arcs, which include the entire circle, that means that the sum of these angles has to be 180. And that's where this theorem comes from. Opposite angles of an inscribed quadrilateral are supplementary. The next theorem involved involving polygons that are inscribed in circles is this one, Theorem 94. If a parallelogram is inscribed in a circle, then it is a rectangle. Now let me show you why this works. If I happen to know this is a parallelogram, I know that the opposite angles have to be congruent. Now, by Theorem 93, not only do they have to be congruent, but they also have to be supplementary. So that would mean that if each of these is exactly the same, and they add to 180, that means this. They're both congruent, and they are both 90 degrees. Okay, well, that's great. Now, let's mark these as right angles. I know that these are right angles. Now further, because it's a parallelogram, I also know consecutive angles are supplementary. So now that I have those right angles, I know the other two have to be right angles as well, and that makes it a rectangle. Now we're going to start talking about power theorems. Power theorems have everything to do with how segment lengths relate to circles. So Theorem 95 says this: if two chords of a circle intersect inside the circle, then the product of the measures of the segments of one chord is equal to the product of the measures of the segments of the other chord. They call this the chord-chord power theorem. I like to look at it like this. I see these two segments, these two chords crossing here. I think about it like this. The product of the pieces is equal to the product of the pieces. So I usually will just think about it like this. Piece 1 times piece 2 is equal to piece 1 times piece 2. So we're just multiplying the product of the pieces and setting them equal. The next power theorem says this: if a tangent segment and a secant segment are drawn from an external point to a circle, then the square of the measure of the tangent segment is equal to the product of the measures of the entire secant segment and its external part. They call this the tangent secant power theorem. I like to think about this way. Outside times whole is equal to the outside times the whole. So if you look at the picture I've drawn, if I look at this top segment here, this is my tangent. The length that's on the outside is A. The whole segment length is also A. Now if I look at the bottom segment, the outside part is B. The whole segment is B plus C. And that's where we come up with A squared equals B times quantity B plus C. Now, the next theorem, 97, looks very similar to 96. It says, if two secant segments are drawn from an external point to a circle, then the product of the measures of one secant segment and its external part is equal to the product of the measures of the other secant segment and its external part. They call this the secant-secant power theorem. Now, the last phrase that I said was outside times whole equals outside times whole. And this works for this theorem as well. So if I look at my top segment, the outside part is A. The length of the whole segment is A plus B. If I look at the bottom segment, the outside part is C. The whole segment is C plus D. And that's how those segment lengths relate. So looking at this picture, I want you to give this a try. I'd like you to use the theorems that I just talked about to find X and also to find Y. Press pause on your video, and when you're ready for the answer again, press play. Okay, here are my answers. I first found X. So I knew that I had two chords intersecting inside a circle, so I was thinking about it as the product of the pieces is equal to the product of the pieces. So 4 times x is equal to 3.2 times 10 here. That gave me 4x equals 32. Divide both sides by 4, x is 8. Now that I have that, I'm going to be able to find y. So again, I'm thinking outside times whole equals outside times whole. Looking at my top segment, x is my outside, not x, sorry, 6 is my outside. The whole segment here is 6 plus 8 plus 4. From the other segment, the outside is y, the whole segment is y, so I know that's equal to y squared. This finally simplifies down to 108 equals y squared. I took the square root of both sides, and I simplified, and I found that y is equal to 6 square root of 3. I'd like you to try this problem. Press pause on your video, and when you're ready for the answer, press play again. All right, so I found y first, and I said the outside times the whole is equal to the outside times the whole. Y squared, outside times whole, is equal to the outside 5 times the whole, 5 plus 5.4. I simplified down to getting y squared equals 52. I took the square root of both sides and got y is equal to 2 square root of 3. Now I have that. The next thing I did was I found x. Same kind of idea. Outside times whole is equal to outside times whole. The outside 4 times my whole segment, x plus 4, equals the outside 5 times my whole segment, 5 plus 5.4. Simplifying it down, I had 4x and distributing the 4. 4x plus 16 equals 52. I subtracted 16 from both sides, and then I divided both sides by 4, and I found x was 9. So that concludes my explanation for sections 10.7 and 10.8. Have a nice day.